Alright, hey everyone, welcome to the last segments of the higher order differential equation module that we have been discussing for a while now, right? This is where we apply what we learned so far to the engineering application, okay? The first thing we will analyze will be actually something that you've been doing for quite some time now, and you know this. It's called Newton's second law. You know, F is equal to ma, right? You know this, right? Obviously, this force is an external force. So, and if you, well, you also do know that this is dv dt, isn't it? Which is the acceleration, which is also m times, and the velocity itself is the derivative of the displacement. So you can see that this is going to be the x squared dt squared, right? Because this itself, the v itself, is dx dt. So now what I will do is I will look at a very common mechanical engineering approach that we take, and it's going to be the spring mass damper system. ma is equal to, if you have a spring mass damper system, here is what it's going to look. You know this. Hooke's law, right? This is the spring. K is the spring constant. How about this? You may or may not remember this. This beta is a damping coefficient, and this is the damper component. Okay. And one thing to note is this is dx dt. What is dx dt? It's up there. It's going to be the velocity, right? Beta times the velocity. Plus, I can have some additional external force. Nobody's going to stop me from having that, right? So external force, let's call this damper, let's call this spring, so we are all on the same page. And if I go ahead and draw this, let me draw this way. It doesn't have to be perfect. So I have something like a spring over here. Then I have some type of a mass, right? And then this is connected to a damper. So basically, this is coming from my side, right? The fluidic stuff that puts the damping into the play. So you can see this is the damper component. This is the mass. This is the spring. And I have, let's say that this is the equilibrium point of x is equal to 0. And I can have, I don't know, I can have f of t in any direction, right? Nobody's stopping me from doing any of these. Let's rewrite this and have some type of a differential equation so we can solve it, right? That's the whole point why I'm, discussing that. So the first thing that you may wanna, you should already see is that, I need to leave this alone, right? Do you remember that? I need to leave this alone, so I'm gonna divide everything by mass, and well, let's do it. And I will get myself d squared x dt squared. And if I divide the right hand side, I'm going to have k divided by m minus beta by m. And this is going to be dx dt, right? Plus ft per unit mass, right? And we have specific terms for these. I'm going to call k by m is omega squared. You may ask me, why is there a square over here? Well, that's by convenience. You may remember that we were talking about this sine omega t, the harmonic oscillation and all. So for us to be on the same page, so we put this over there, okay? For the same kind of logic, I'll have this beta by m is equal to 2 lambda. Again, you may ask, well, why is there 2 over here, right? Why didn't I say square over here? Well, because you will see that when I have an equation that I formed, a differential equation, the auxiliary equation I wanted to look much more convenient for me to solve. That's the reason, okay? And this will determine the overdamped, the critical damped, underdamped systems. And ft by m, we call this f of t, the capital. When all said and done, I'll actually take this side as a plus. I'll take this side as a plus, and I'll leave it to here. So that will look more like what we've been working with, right? So the final equation that we have is going to look like this: 2 times lambda dx dt plus omega squared x will be equal to f of t, right? So this will be my differential equation that I need to look at, okay? So this is the most involved one, and including our textbook, all of the textbooks do it in multiple steps where they look at, let's say that I have an undamped motion, right? So what that means is this beta is 0, right? Or we can call this unforced motion. So at that time it will be a homogeneous equation. F of t will be 0, okay? But I don't really need to. What I want to do is I want to solve this case, and you will see at the final I'll get a very complicated, and you simply put beta is equal to 0 or lambda is equal to 0 if you choose to. Okay, obviously it will be much easier to solve. If this is homogeneous, well, if I solve this equation anyways, I'm going to solve the homogeneous, and then I'll get a particular and sum them up. Remember that? So I will also solve this anyways. Okay, so I don't have to cover this separately. I'll cover this case, and you can interpret from here what it means for you if I have, let's say, that a free damped motion, right? Free damped motion. Okay, it's damped, but the free means that f of t is 0, so you will have, like I said, homogeneous equation over here, right? Or you can have free and undamped. Free means 0 over here, and undamped means this is 0 here, and this actually looks much more easier to solve, right? And I actually can see why there's a w squared here for the solution. As I covered all the fundamentals approaches for solving higher order differential equations, this application is fairly doable. Okay, it will be actually much easier than the questions that I've solved. They may be longer, granted, they may be longer, but it's not going to be as complicated as what we've been dealing with so far. All right. So, I mean, the best way to do is just to start with an example. Okay, let's say that I'll give you some numbers, so we will play with it. So let's say that the mass. And I haven't been doing this British gravitational units. So let me go ahead and have a question like that. Okay, I will have mass of 1 slug, and obviously this is attached to a spring. I'll give you the spring constant as well. So the spring constant will be 5 pounds per foot. So that will be my K value, right? And what I said over here, do you remember that? I said that this is initial value problem. So in order to have an initial value problem, I need to give you some initial conditions, right? So I will give you some initial conditions. Let's say that the mass, and let's say that this is the, this is the equilibrium point, and I will first move it, like, let's say 1 foot below it, okay? So I'm starting over here. So the x0 will be 1 foot, so I'm going to start 1 foot below from the equilibrium point. And actually, why don't we just hit it off with a velocity of 5 feet per second? Okay, so what I did was, just to highlight, this is the mass, and I have over here, this is the spring, right? And I have damper and etc. down there, the way that I draw. And I'm just pulling this down, right, to 1 foot distance, and I'm just pushing it with 5 feet per second. So that will be my initial condition. Okay, and let's say I don't want to give you the beta, but I want to read it so you can understand what a beta or lambda is. Damping force numerically equal to 2 times the instantaneous velocity. Okay, so if I go back over here, I wrote the forces, summation of the forces over here, right? These are the summation of the forces. I'm going to read this, and I want you to look at this particular term. What is dx dt again? Velocity. He is saying that the damping force is numerically equal to 2 times the instantaneous velocity. So this beta is 2. That's what I meant to say. So I'm just making it a little bit more involved, so to see whether you are aware of the steps. And let's put a forced motion. Why not? And let's make it a little bit more complicated, so the equation isn't as simple as a basic equation. Okay. So basically, this is the question that we have. Let me read it one more time. I have a mass of 1 slug, and I have a spring constant of 5 pounds per foot. And I have this initial condition is I am releasing this 1 foot below the equilibrium point, and I am actually downward wise. I'm adding 5 feet per second initial velocity, and I have a medium, and this medium offers twice the instantaneous velocity as the damping force. Okay, and I am giving an external force of 12 cosine 2t plus 3 sine of 2t. And my goal is to find the equation of motion. What is the equation of motion for this particular case? I have the equation over here. So let me see how am I going to obtain my lambda, how am I going to obtain my omega, and etc. So I can put it in and I get myself a nice equation and go for it, right? And the rest is, solving a second order differential equation. So, okay, so here is what it says. If I go up here, right, when we convert it, let's start with the lambda, right? So I have this beta over here, and I have this over here, right? So I'm going to divide that, I have my beta, which is 2, right? The mass is 1 slug, so I'm going to divide 2 by 1 is 2. So 2 lambda will be equal to beta divided by mass, right? So that's going to be 2 by 1, 2. That's what we said, right? How about the omega square? Remember that it's k by n, right? So that will be k was 5, so divided by mass is 1 slug, so I'm going to get myself 5, right? So and then if I write the equation of motion, it's going to look like this then, d square x dt square plus 2. Don't write just lambda over here, just want to highlight. Lambda is 1, right? But I don't want to write 1 here, I'm going to just write 2, right? Careful. Dx dt, which is the velocity, plus 5x will be equal to, the right hand side is the force, 12 cosine 2t plus 3 sine 2t. I'm not sure I'm going too fast, but I'm simply rewriting, 2 lambda was 2, this was 5, the whole thing, and the right hand side was right here. So I simply inserted to the equation. And is this a difficult question? No, not at all. This will be very doable. You'll find out, okay? But, before we get excited, as engineers, we get excited about looking at these kind of things, right? So let's not still forget the fundamentals, how we are going to apply this. The first thing that we must do is basically the y will be equal to yc plus yp. Let's not forget that. So the first thing I'll do is I'm going to solve yc. And if I write the auxiliary equation, you will see that I will get myself m squared plus 2m plus 5 is equal to 0. So now what I will do is minus b plus minus square root of b squared minus 4ac divided by 2a, right? That thing. I have been practicing this for a while, so I'll simply write it. Minus 2 plus minus square root of b squared is 4 minus 4 times ac is 5. So you can see over divided by 2. I will get myself minus 1 plus minus 4 minus 20 is 16, square root of this 4, so divided by 2 is 2i, right? So this will be my alpha, this will be my beta, right? Now let's be careful about this beta. I'm not talking about the damper, right? Complementary solution. So let's call this xc is going to be e to the power of minus t, right? Because alpha is minus 1. c1 sine of 2t plus c2 cosine of 2t, right? Again, this is not that, we discussed this several segments ago, so not that bad. So now I will go ahead and solve the, obviously, particular solution, right? Particular solution. So as these are all look at these are all simply numbers over here, so I have several methods to, I can approach this, right? I can do the undetermined coefficients. I can also do the variational parameters if I choose to. But I kind of like the undetermined coefficients. It's a bit longer, kind of like that. So I'm going to go with what I like. So, but you don't have to, obviously. Okay. So if I do that, let's look at the right-hand side of the equation. So do you remember what this form of the yp should be given that? Yeah, I do know, actually. It's going to be a cosine of 2t plus b sine of 2t. Okay. So if I go up, you'll see I'm replicating this cosine of 2t, and I'm going to replicate this sine of 2t. I have this a and b, and the goal is to find the values of a and b for this particular solution. So we'll do xp prime, because I'm going to need that, obviously, minus 2a sine of 2t plus 2b cosine of 2t. I'll do one more derivative, because I need this. So I'm going to have minus 4a, now sine cosine, right? And this time around, this will be 4b sine of 2t. Okay, so that doesn't look too bad now. So if I go back to my equation that I have over here, so it's going to be basically the first thing I'm going to insert this, and that is that. So let's simply rewrite this. Let's start in page 4a, cosine of 2t minus 4b sine of 2t. So that is the second derivative of this xp. And then I have plus 2 times the velocity, which was minus 2a sine 2t plus 2b cosine 2t. Okay, let me go up, I'll show you. So I simply went ahead and multiplied with dx dt, it's right here, right, dx dt. I just plugged it in, and 5 times x. Then I'll add this 5 times itself a cosine of 2t plus b sine of 2t will be equal to 12 cosine of 2t plus 3 sine of 2t. Obviously, you kind of know what I will do because we have experienced this, but I'll do this cosine of 2t plus sine of 2t for the left-hand side, and I'll equate this to, the cosine 2t, this will be 12, this will be 3, right? That's what I'm going to do. But let's take a look at it. So cosine of 2t. So that's going to be minus 4a, I can see from the very first term. So let's cancel this out. I can cancel this out. That's going to be plus. Don't forget the plus because you're multiplying by plus 2. It's going to be 4b. Let's look at the last term. I'll get 5a. Let's look at the sign. That will be, this is gone, this is gone. Let's not forget. Minus 4b minus 4a. I ran out of space, so let me erase this. Plus 5b. And I'm saying that this will be 12. This will be 3. The left and the right hand side of the equation should be the same, right? That's the solution. So you can see here, let's do some manipulation. A plus 4b is equal to 12. And over here I get myself 4b plus b minus 4a is equal to 3. Why don't I go ahead and multiply this by 4, right? This whole thing. So I'll get myself 4a plus 16b is equal to 48. Do you see if I sum them up side by side, these 4a's will cancel. I'll get 17b is equal to 48 plus 3 is 51. So you can see from here b is 3, right? So if the b is 3, so this is 3. Now 4a is 0, right? A is equal to 0 then. So now I get myself my XPS 3 times sine of 2t. The cosine term dropped out. One thing before I write the final answer, you may be thinking, maybe you do, I don't know. But do you remember I can't have the same form between the complementary solution and the particular solution, but I did go ahead and do it. Did I make a mistake over here? No, because you're forgetting this. This whole thing is multiply e to the power of minus t. If this was 1, yeah, then you have to multiply this by x. So it's going to be ax cosine 2t plus bx sine 2t, right? Just want to highlight one last time before we finish off this segment. But now I will simply go ahead and sum them up. So my x to total equation of motion solution will be e to the minus t, c1 cosine 2t plus c2 sine 2t, well, plus 3 sine 2t. Am I done? No, not if you want the full credit, obviously. Why? I didn't even use this. Look, I have x0 is equal to 1 foot, v0 is equal to 5 feet per second. So I didn't even use that. Why don't I use that to find these two? So I should be able to solve this equation, so that makes me happy. So let's do this x of 0, right? So let's see what happens. It's going to be plus 1, that's what is given to me. So if I go in here, what is sine of 0? That is 0, so that's out. That is out. So from here, this c1, what is cosine of 0? 2t, which is t is 0, so it's going to be cosine of 0 is 1. So I will have my, well, 1 is equal to c1. That's exactly what I got. So it was kind of easy. Okay. So now let me go back and write this. So my x is equal to e to the minus t, well, cosine of 2t plus c2 sine of 2t plus 3 times sine of 2t. Good. So the next is going to be the v0 is equal to 5. So basically what it means is x0 prime at 0 is equal to 5. That's what I mean, right? The velocity. So now I have to go ahead and take the derivative of that. Okay, this whole term. So let's go ahead with it. So let's take the derivative chain rule. Let's first start with taking the derivative of this term. And you're going to have minus e to the t, and the right hand side second term will stay exactly it is. Sine of 2t, right? But then I'll have plus. Now I'll take the derivative of that parentheses, so it's going to be minus 2 sine of 2t plus c2 times, so it's going to be 2 times c2 times cosine of 2t. And what about the very last term? Let's not forget that. That's going to be 6 times cosine of 2t. Okay, then I'm going to insert t is equal to 0. 5, left hand side, is equal to e to the 0, that's 1, so there's a negative sign, let's not forget that. That's going to be minus cosine, that's going to be 1, sine of 0 is 0, plus, again, 1 times 2c2, well, plus 6, right? So what is going on in here? So let's take a look. So these three cancel. So I get myself c2 is equal to 0. So then it means that my x will be at the end of the day e to the minus t cosine of 2t plus 3 times sine of 2t. So this will be my displacement as a function of time. Okay. Now I'm going to look at the series circuit analog. Okay, LRC circuits and all. I'll be right back. Thank you.